All right. Last time we finished at the previous slide. We had a lecture, you remember, on DC motors. So it was lecture 4 on DC motors. And we finished on, let me remind you, we looked at how the motor works. So on this part, right? We also looked at the mechanical model, electrical model. So we got overall model in time domain, in Laplace domain. We got a Laplace model presented as a transfer function using this transformation that involved inverting a matrix. Okay. So this was transfer function from U to omega. We also saw a state space model. We saw this transfer function for from voltage to angle, from angle to angle, okay, and state space model for the same. All right, so this is where we left last time. Now, for today, we have to continue. There will be a few slides in this lecture and a whole lecture on the properties of motors. So let's dive right in. First, let us consider the effects that the payload would have on the model. Okay. So let us consider a payload with a moment of inertia J sub p and torque tau p. Okay. So what is a payload? Is something that your motor essentially moves. Just to give a few examples. So, for example, let's say you have a inverted pendulum. Well, then the pendulum itself on the end of the motor. Inverted pendulum then would be a payload. If your motor drives, let's say, for example, a fan that produces airflow, that fan would be a payload. Okay. There are, if it is the motor drives a wheel, the wheel will be a payload. Right? Okay. So what do I mean by then moment of inertia? Moment of inertia is the definition is from mechanics. So moment of inertia defines for 2D motion at least, defines a ratio between the torque that is applied to an object and the rate of change of angular velocity. So moment of inertia for a payload means given a torque applied to the payload, what rate of change of angular velocity can you expect? The inverse of this coefficient would be the moment of inertia. Okay. Okay. Now, what is the torque of moment of inertia? Well, this is a more difficult thing. You can think of it kind of similar to how we were considering characteristic equations of elements. So basically, for example, for a fan that blows air, the torque may be proportional to velocity with which the fan moves, or it can be proportional to the square of the velocity with which the fan moves. This will be the torque that the fan applies back to the system, you could say. Or in a simpler case, it can be the torque can be proportional to the gravity for the inverted pendulum. Okay. All right. So this is kind of like a simplistic way of talking about it. Okay, let's just look at the math. So here is our well recognized by us electric equation. So Kirchhoff voltage law. Okay, nothing changes. This is what we saw last lecture. This is our effect of our inductor. This is the effect of resistor. Both of them physically one and the same, right? Inductor both have inductance and resistance. Here is our back EMF. Here is our voltage that drives the motor. So all of this familiar. Now, time to go to the mechanical equation, which is different. So here's the rate of change of angular velocity. And for it, we have, in front of it, we have a sum of two moments of inertia. Moment of inertia of the motor plus the moment of inertia of the payload. The way you could visualize this is by thinking of a motor. Here's I'll quickly try to draw how the motor looks. Okay. And here we have a shaft, output shaft. Okay. And imagine at the end of the shaft you have a payload. Okay, I will draw it like this. You can say the motor of inertia is you can say that total moment of inertia is the sum of the moment of inertia of the motor itself, so the shaft, for example, like anything that moves inside the motor, plus the payload, right? It makes sense. Like everything that moves contributes to this inertial property of the system, right? And somehow this is represented here by summation. Okay, we'll be more accurate in a few slides. We'll understand it better. Okay, but here you can say this is direct summation. All right, good. Indeed, it makes sense if you think of it in this picture, right? If let's say, if you think that J is the moment of inertia of the shaft, and J sub P is the moment of inertia of this object, right? This payload, then it makes perfect sense. So it will be summed. Right? All right. Now this guy here is effect of friction, viscous friction. So friction that is proportional to the velocity. This is our torque generated by the motor. So it is proportional to the current. Okay. And here finally we have this payload torque. So torque that is associated with the payload. Okay, I think it will be even more clear when we consider example. So example is pendulum, right? With a mass m and length l. Right? How? What does it give us? Well, the first equation is exactly the same as before, so nothing changes. The first equation, let me show it like this, okay, is the same. Here we have the second equation. We have our original moment of inertia plus moment of inertia of a pendulum. Here I consider the pendulum as a unit mass on a at the end of the shaft without a weight. So what we can call mathematical pendulum. So weightless shaft and the mass at the end. Right. Okay. Now next we have exact same friction, right? We have exact same torque produced by the motor, which is proportional to the current. And here our payload torque is the same. It is mass times. Yeah, it is the same, but here it is opened up. Okay, so what is it? It is a gravitational force, so mass times gravitational acceleration. This is the force that produces torque. And here times L sine phi. This is the what we can call this is the distance between the direction of the force and the axis around which rotation happens, right? So, for example, here we have axis of rotation applied here, right? This will be where the motor is connected. We can draw a vertical line, right? The force acts down as the gravity does. So this distance would be L times sine phi, if phi is this angle between the horizontal and the pendulum, and L is the length of the pendulum. Okay. Good. So this is a particular example. As you can see, essentially, the second equation, it can look complicated, but it simply discusses the same mechanical system, but with more details, right? Before it was just a shaft rotating under torque with some friction. Now this shaft is still with the torque and the friction, but also with the additions, right? Like with the pendulum rigidly attached at the end. So this changes inertia, and this changes torques. So external, for example, gravity force externally acts on this system. Okay. So this is what happens with the payload, right? Another thing that can be attached to a motor is a reducer, or a gearbox, gear system, transmission. It's a little bit hard for me to choose best word out of all English words that we have. So I apologize if I use suboptimal English to describe what I mean. A Russian term for this would be reductor. Okay, so that's why I'm sticking to reducer. I'll be happy to optimize the terminology. Okay, so a reducer. A reducer is a mechanism for reducing angular velocity of the output shaft of the motor while increasing the output torque. You could say, especially if you have like a mathematical attitude towards the subject, that reducer can also increase the angular velocity at the expense of reducing the torque, output torque. But in practice, this is extremely rare. So almost always reducers specifically reduce angular velocity at the advantage of increasing the output torque. So this is very typical, because usually output torques are comparatively low for almost all motors, while the angular velocities are comparatively high. So it almost never makes sense to make some angular velocity even higher and torques even lower. In fact, the opposite is the case. It is almost always advantageous to reduce angular velocity, because tasks don't usually ask for such a high angular velocity. Be it like a motor that drives a wheel of a robot, be it a motor that drives your robot arm, or almost any other thing, the angular velocity is almost always sufficient or even too large. There are notable exceptions, such as drones, which do not use reducers. For them, angular velocity is exactly fine. Same as for a lot of other systems which have to do with running fans, propellers, and so on, where the torque, comparatively low torque, is at the same time fine, it is okay, and the angular velocity is what we want to keep. So those systems don't ask for a reducer, but most others do. Okay, so a reducer reduces angular velocity and increases torque. Okay, this is achieved by using gear systems, but we will discuss this in detail later. For now, let us just think of it as a mechanism for reduction of angular velocity and increase of torque. Okay. So let us define angular velocity of the output shaft as V sub omega sub O, okay, omega sub O, and torque of the output shaft as tau sub O. Okay, so ideal reducer acts in this fashion. It says that the angular velocity of the output shaft is equal to the angular velocity of the motor, okay, angular velocity of the motor, divided by the reduction ratio. So as we said, it is all about reducing, right? So it is divided by the reduction ratio. N is a number. It is bigger than 1 number. So we divide by it, we get output shaft angular velocity. Okay. Output torque is multiplied by this number. Okay. It is multiplied by this number. So whereas angular velocity is divided by this number, torque is multiplied by this number. This somehow makes sense, right? We said angular velocity is reduced, and the equation 22 tells us how much it is reduced. Well, by the factor of n, right? Well, torque is increased. How much it is increased? Again, by the factor of n. So somehow it's symmetric, it makes sense, it is balanced. Okay. Now, the key idea of ideal reducer model is that we could model orientation velocity of the input shaft and the output shaft using same coordinates. Let's look at this for just a second to understand what I mean. So here is the internal shaft of the motor. Okay, so this is what sticks out directly out of the coils, which makes rotation. So this is the internal shaft of the motor, and here's the output shaft of the motor. Okay, this is what sticks out of your whole system. Okay, so you have a motor, you have various gears, and out of the last gear, you get axis sticking out. Okay. Not even axis, shaft, motor shaft. Okay. Just for your information, we often think of axis as something that doesn't rotate, that something rotates on the axis, and gearbox shaft is something that rotates itself. Okay, so those two are different things, right? This omega describes something internal to the motor. This omega describes something external. Okay, but we can replace one of them with the other. Okay, we can use one variable to discuss both of them because they're proportional, and the coefficient of proportionality is well known, 1/n. This is the whole point. We can still discuss a motor as before without introducing more equations or anything like that. As soon as we need to discuss output variables like output velocity, output torque, we simply can stick this 1/n or n into the equation in the appropriate spot, and we will get those quantities. We don't need to introduce new variables. That is the idea of an ideal reducer. All right. We'll see more about it in a bit. Now, let us consider important question. That question is quite important for design, but for various things. And that is, what happens with the payload inertia attached to the output shaft of a reducer? Okay, so now this is the involved question. I'm not sure if it is easy on the first try to even understand what we are talking about. So consider motor. I will draw it schematically, but this is a motor, okay? Here is the output shaft of a motor. Let me, I guess, 1 second, let me make a white space here. All right. So here's the output shaft of the motor. Okay. Output shaft of the motor. Here is a reducer. Reducer, we often write it as denoted by N. This is just typical way to denote reducers by letter N. Okay. And at the end of this reducer, you have output shaft, right? So we understand the relation between, let's say, angular velocity here and angular velocity here. It will be 1 over n. Okay, that we understand. But what happens when at the end of this shaft, we have a massive body with inertia, okay? So what happens? How do we write equations of the dynamics when we have this situation? This is not clear, right? You could say maybe we could just sum both of them, like as before, right? We can say we take inertia of the input shaft, inertia of the output shaft, sum them, and this is fine. This is not necessarily fine. And let me show you why it isn't, okay? So we consider a payload with inertia J sub P. And again, angular velocity of the output shaft would be V sub O. Okay. Now, what I'm going to do is to write kinetic energy of the system. Kinetic energy of the system. This is a key idea. How do we compute inertias? We have to consider kinetic energy. Very, very important insight, here. Kinetic energy. All right. So kinetic energy consists of kinetic energy of the internal shaft. So kinetic energy of this guy here. Well, I guess let me color code. So I will just use dark green. Oops. I use dark green here. So this is the kinetic energy of the internal shaft of this guy. In practice, this guy actually exists. It's not just like mathematical entity, this internal shaft. It will be some actual shaft that goes through the whole motor like this, like the way I draw it. Okay. It'll be, let me do it like this. Okay. So there will be some, it will be inside the motor. Okay. All right. And then we have additionally kinetic energy of the output shaft together with the payload. All right. So it will be kinetic energy of this guy. Okay. Output shaft and payload, which we agreed is the inertia of this guy is J sub P. Okay. Notice the important detail. Important detail is this. While in the kinetic energy associated with the input shaft, angular velocity is omega squared. For the output shaft, it is omega sub O squared. So two different angular velocities, okay? It's not the same because the rate of rotation for them is different, right? One is fast, internal shaft, one is slow, external shaft. Okay. But we can transform it into one variable, right? As we said before, this is why we have this ideal reducer model, right? Because we can transform. So we keep this the same, right? The equation for the internal shaft. But the equation for the output shaft we transform by replacing omega sub O by omega over n. So we have n squared here. and we have everything else the same, right? This is the same equation as before, just with divide by n squared. But now it is omega, not omega sub O. So now it is the same variables, okay? And now, final step, we can get omega squared out of the brackets, okay? And I guess we can also get 1/2 out of the brackets. So we have 1/2 here of omega here. And what we have inside the brackets is j plus j sub p over n squared. But this is inertia. Kinetic energy, by definition, is structured this way. It is 1/2 inertia omega squared, or angular velocity squared. This is a rotational inertia, rotational kinetic energy. So it has to be 1/2 times inertia times angular velocity squared. And nothing changes, nothing changes. It is the same. The same is true here. So it is, 1/2 inertia angular velocity squared. So this guy is inertia. So inertia in this equation would have this form: j plus jp over n squared. That is inertia. And it somehow makes sense, right? This division by n squared, when we have a reducer, means that for the angular velocity rate of change of angular velocity, it is like this outside mass that would have prevented it normally isn't as effective because of the reducer. And of course, it isn't as effective because this reducer effectively does this outside mass experiences 1/n of angular velocity of the input shaft. Okay, so the reduction of this coefficient, the rate of change would also be 1/n, right? So of course it shouldn't be like the same torque should have more potency. As we said, torque acting on the output shaft is n times higher. So the output in terms of output shaft, we expect it to be less important. Less important its inertia. We could rewrite all this equation in terms of omega sub O, and then n squared would appear in front of this guy. It would just be multiplied by n squared. And this again would kind of make sense, because then what would happen is we would say internal shaft of the motor is much more important because it rotates n times faster. And any change of angular velocity would be n times higher there than the output shaft. So this is what's going on here. Okay. All right. So this is about moment of inertia, right? This is how we compute it. There is one interesting also thing here, and it is this, right? As we said, payload, so output shaft torque is equal to internal torque times n. So vice versa is also true. The internal torque will be equal to the outside torque divided by n. It works to see how the payload acts on the internal dynamics. It acts n times less than internal torques. So, for example, this friction force, which may be small, negligible, but because it doesn't have a reducer in front of it, it acts directly and it is potent, while the outside forces would be much less potent, depending on how big N is, right? So this is, again, the situation. And now I guess you can even see why we like reducers, why we use them so much, right? Reducer here makes sure that the inertia of the payload is not as effective. It doesn't do much, right? Especially high reduction ratio will make sure that it is almost negligible. And outside torques become almost negligible. Of course, they cannot be completely negligible, right? But they can be quite small. And that is nice. Especially if we don't know those torques in advance, and we want them to be kind of close to negligible, high reduction ratio would do that. So if you for example, if you can expect 100 newtons here, plus or minus 1 newton, right? So 100 newtons is what you expect, plus or minus 1. This plus or minus 1, if it is divided by, let's say, a factor of 100, it will be plus or minus 0.01. Not so much, right? Not so much. So it's quite small, quite a small change. And that is, why a big motor with a big big reduction ratio would not feel much the change of payload, right? Because it is going to be made small by this reduction ratio. Okay. Right. This is it from last lecture that we didn't complete. Those links provide you interesting and nice information. So if you want to self-study, I recommend those. They're very good links. So very good papers, articles, and so on. So take advantage. Okay. Let me do this.